All right, so again, we already discussed this. So now, since you are okay with linear equations, then let's keep looking at linear equations, but let's introduce a new word, rational equation. The word rational stands for fractions are popping up. Okay, so let's look at similar equations, but now there will be fractions in the mix. So now, a rational equation is not exactly the same as a linear equation, just because when you have a rational equation, now variables may show up in the denominator. You know, rational. The word rational means you're gonna see fractions, but maybe the numbers are the ones that are fractions, and the variable stays as we have been seeing, so still linear. But you could have a fraction with a variable in the bottom. Now that's no longer a linear equation. Okay, it's an honest rational equation. Anyways, let's keep going. So let's see. I'm gonna keep putting examples here, and then I will explain, and then let you work, etc. So 5, 6. For example, 5 and 6 are still linear. Because yes, there are little fractions, but the fractions are in the coefficients. The variable itself is still, by itself. So there's nothing strange happening with the variable. And now number 7, slightly different. It's no longer linear because now we do have a variable down here, the denominator. Okay. Let's make it slightly more interesting. So for example, 7, 8, and 9 are no longer linear equations, but they are rational equations, okay? But what happens is that we're gonna do something that's gonna turn these equations into linear equations, okay? So the way you solve this is you do something to this, it's gonna turn them into linear. Sometimes you could get something quadratic, but in these examples, we get linear, we talk about linear. So we do something to this to change it into linear, and then we solve it like a linear equation, okay? As you will see. All right, so I guess, let's see. I'm going to explain number 5, then you do 6. I explain number 7, easy one, and you do 8. It's more interesting than 7. And then we'll explain 9 as a whole, okay? All right, so let's do this. Solution. So when you're working with rational equations, you have to be careful, okay? For example, when you have a linear equation, there's nothing to worry about. You just start solving, and if you get a solution, you know that's a solution. If you get x equals something, that's a solution, okay? Or you may get everything or nothing. But when you have rational equations, 5 and 6 are okay because those are linear. But when you have rational equations like 7, 8, or 9, you have to worry about some stuff. The equation itself has limitations. The equation itself is telling you that at some values that x cannot be no matter what. For example, let's take a look at number 7. Can you tell me a value for sure that x cannot be? Very good. Remember, when you have fractions, the bottom cannot be 0, the denominator. So this is telling you that no matter what you do, you better not get 0 as an answer. If in your work it turns out that you get x equals 0, you need to understand that that's not a true solution. We call that an extraneous solution. Okay? So you have to keep that in mind. For number 8, what's the value that x cannot be for sure? 2. And for number 9? 3. So you should always make a note on that, because what you do is we're going to transform these equations. So when you transform these equations, you're not going to see that problem anymore. And you will be just solving a linear equation. And if you don't keep in mind that you have these restrictions from the beginning, you could be led to give the wrong answer. You understand what I'm saying? So for rational equation, you have to be slightly careful. Don't just jump and start solving. Okay, anyways, 5 and 6 are fine. So let's just do 5. Now, technically something like this, I probably should have done something more interesting. Okay, 6 is already interesting enough. So, okay, so this one, you could do it the way that we have been doing. Like move the 5 over, and then the 3 is dividing, so you multiply, the 2 is multiplying, you divide, right? And you solve for x. You could do that. Now, I'm going to explain to you another way, because that other way, for example, is more helpful for problems like number 6 and so on. Okay, when you have multiple fractions. So if you are comfortable manipulating fractions, that's fine, then you can do so. However, I strongly encourage you to get rid of the fractions in one shot. Okay? So a good idea would be just to do something to this equation so that there are no more fractions anymore. And we can do this easily. All you have to do is find the least common denominator or the minimum common multiple among the denominators. For example, even though you don't see fractions here, you can think of these numbers as fractions, right? You can think of this as 5/1 and 7/1. So focus on all the denominators that you see. We see 3, 1, 1. So 1 doesn't count, just really 3. So what's the minimum common multiple? Do you know what I mean by minimum common multiple? Do you know what's a multiple of a number? So tell me the multiples of 3. 3, 6, 9, 12, etc. That's why a multiple is just this number times an integer, okay? Common multiple, well, they have the same multiples, right? And minimum is the smallest, okay? So among these numbers, what's the minimum common multiple? 3. You understand this? 3 times 1 is 3. Then 1 times 3 is 3, and so on. So 3 is the minimum common multiple. So what we do is we multiply the entire equation by 3. So when there are fractions, the minimum common multiple is called LCD, least common denominator. Okay? So here the LCD is 3. So you multiply every single term by 3. So let me show that slowly. So that's 2/3x times 3 plus 5 times 3 equals to 7 times 3. So remember, these two quantities are equal. So if you multiply both sides by 3, you will still get the same inequality. Okay? So we didn't really modify the solution to the equation. This equation look different, but they have the same solution. They're equivalent. So now what's going to happen is that this number is special. This number is guaranteed to get rid of any fractions that you have here. Okay? In this case, there's only one fraction we have to worry about. Now, you know how to multiply fractions? Yes? So remember, when you multiply fractions, you do top with top and bottom with bottom, and then you simplify. Or you can simplify first. Make sure that anything on top can be simplified with anything that shows up in the bottom. Okay? So remember that there is a secret 3/1 here. So that means that this 3 cancels this one. Okay? And that's it. There's no more cancellation. So this turns into 2x plus 15 equals 21. So by multiplying by 3, we turn the above equation into this one, which is a regular linear equation like the ones that we have been dealing with. Yes? No more fractions, now you just solve it. So subtract 15, so what do we get? 6. And then we divide, we get 3. Questions? And indeed, you can see if you put x equal 3 here, the 3 is cancelled and you get 2 plus 5, which is 7. Okay? Did you understand the idea? So if you see fractions, I recommend you multiply by the LCD just to get rid of the fractions. Okay? And then you solve the resulting equation. So go ahead and do 6. What's the LCD in 6? Yeah, 6. In problem 6, what's the LCD? 6. That was a coincidence. Okay, anybody has an answer for number 6? Yes?
31/4.
31/4. Is everybody getting the same thing? Okay, good. All right, so let's see, let's do it. So 2 over 3x minus 5 equals 1 over 6. And everybody agrees that the LCD is 6. Yes? So I'm going to multiply every single term by 6. So let's see. Is everybody comfortable? Is it okay if I just write the next step? Oh, so I'm just going to do all the steps, even though you already know, just in case. So 1 over 6 times 6. Now, notice that here, now we just simplify. So the 3 cancel with the 6, but it's going to leave me with a 2 up here. Okay? And then multiply that. So 3 cancel with the 6, leaving you a 2, a 6 divided by 3. So we get 4x minus 30 equals 6 cancel out. So you get 1. And now we are in business. Move the 30 over, positive, and then divide by 4. Good. Questions? Okay. Now, the same here in this case, our denominators have been numbers. But if your denominators are variables, it's exactly the same idea. Okay? You just get rid of the variable by multiplying by the LCD. Now, you know how to find LCD when there are variables involved and not just numbers? Like, for example, if this would have been, say, x minus 7. Do you know how to find the LCD? Something like this? No? Yes.
You multiply all of them.
Very good. So, for example, if you look at the numbers, yes, 6 is the one that works. I mean, it's the ideal candidate for. Let's look at problem 6. LCD, the LCD is 6. So 6 is the ideal, the optimum number that you can use to cancel denominators. You can use another one. You could use 12, right? Because 12 can be divided by 3 and it can be divided by 6, or you could use 18. All right, 18 can be divided by 3 by 6, and notice that 18 is a product of these two guys. Okay, it's just that it's not the optimal one. But when you have variables in the denominator, what you can do is you can just go ahead and multiply it. Okay, that's an expression, and that expression is guaranteed to simplify all the denominators at once. Okay, now how do you know that you have the optimal at hand? Let me, I guess, explain this with numbers. Yeah, the reason why I didn't put an example like this here is because this is we're gonna end up with a quadratic equation. We are not talking about quadratic equations yet. Okay, so I'm gonna erase this soon, but you need to know how to deal with this. But let me explain with numbers. Let me make, I guess, sign off here. So between 3 and 6, if you want to find the LCD, here is what you do. So here is 3, here is 6. You write the prime factorization. 3 is just 3, right? 3 times 1, there's nothing more. Now 6 is 2 times 3. Okay? And then to find the LCD, what you do is every single prime that you see, you write it down. So I see a 3, I write it. I see a 2, I write it. Multiply. And then there's no more primes. And then you go back and look at your prime factorization and look at the powers. Whatever is the highest power, you're going to put it in here. In this case, the power of 3 is 1, so it stays as 3. The power of 2 is 1, so it stays as 1. Okay? And this is your LCD, which is 6. Let's do something slightly more complicated. So let's see. What's the LCD between, let's say, 18 and maybe 45? Or in this case, because these are not really denominators, I should call it MCM, the minimum common multiple. I mean, LCD and MCM is the same, but this makes sense when you have fractions. Here I don't have fractions. So I want to know what's the minimum common multiple between these two numbers. One technique is you can start writing down the multiples of 18, the multiples of 45, until you find a common the first time that they match, and then you found it. But what if you have to do this like 20 times? Are you really going to sit down there and multiply it 20 times? That's not optimal. So you can use this technique. So take your number, each number, and factor it as primes. So let's see, 18. What's 18 equal to?
2.
So just do the first factorization that comes to your mind.
2.
So 2 times 9. But now we need to keep going.
3 and 6.
So then 9 is, so 2 is already prime. Now we can break out 9 more. How can you break up 9? 3 times 3. So this is 2 times 3 squared. Yes? That's the prime factorization. Now let's do the same thing with 45. What's 45?
15, 3.
Okay, so 15 times 3. Now 3 is already prime. Now 15, we can break it down more. What's 15? 5 times 3. So that's 5 times, and then 3 with another 3. That's the 3 squared. You understand this? Okay, so we're ready. So what's the MCM? Okay, let's write down the primes. I see a 2, I write it down. I see a 3, I write it down. I see a 5, I write it down. Now let's come back and let's fix the exponents. What's the highest power of 2 in here? 1, so stays like that. What's the highest power of 3? 2, so we have to put it here. What's the highest power of 5? 1, so stays like that. So what is it? So that would be 10 times 9, 90. So the minimum common multiple is 90. Okay? And now you can do this. Given any two numbers, you can always do this, okay? Regardless of how weird the numbers are. It may take you some time, but you can always find the prime factorization if you need. Once you do this, and then this is the process. Now, this idea, you can do it with variables. Okay? So you just factor all your denominators, write down all your factors, multiplying, and then go back and fix exponents, if there are any exponents. You have to pick the highest. Okay? After you find LCD, you have variables in the denominator. So in this case, so for example, if it was something like this, the first step would be to factor the denominators. It's already factored, right? There's nothing more we can do. And then you just write down the factors. X minus 7, so it will be x times x minus 7. And there are no exponents, so we don't have to fix anything. So the LCD here will be x times x minus 7. Do you understand this? So now, doesn't matter what shows up, you can find LCD by following this procedure. Anyways, I'm gonna get rid of this because this is gonna lead to a quadratic, and we have not discussed quadratics. All right, so here, what's the LCD for number 7? Just x, right? Okay. Because there is only one denominator. When it's only one denominator, the LCD is that denominator, okay? All right, so we have 2 over x. I have some space in here. Let me save space. So we have 2 over x plus 3 equals 2. And then here the LCD is x. Also, as I mentioned, it's good to write down the restrictions. So what are the restrictions on the variable? So restriction means something that the variable cannot be, right? So what's the forbidden value for the variable? 0. So you should make a note on this. Just say that whatever you do, make sure that you don't get x equals 0 at the end. So after that, then just multiply by the LCD. So if we multiply everything by x, then what do we get? What do we get on the left? So we get 2 plus 3x, yes? So this x cancels this one and then multiplies with this guy equals 2x. And then you solve this as usual. So bring the 2x over, so it's going to give you x, and then the 2 to the other side will give you a negative 2. You look at it, you say, okay, negative 2 is not 0, so we're good. Okay, all right, good. So let's see, what do you get for number 8?
3.
What do you get here? Yeah, good. If you put a 3 here, you're going to get a 1, right? And then 2 plus 3 is 5. So 3 works. Now, let's see how we obtain 3. So what's the LCD? X minus 2. Very good. Remember, there's only one denominator, then the LCD is that guy. So multiply everything by x minus 2. So the x minus 2 cancel with the x minus 2 over there, so you just get a 2. But remember, every single term gets multiplied. Again, you could do also, it's probably faster this way. I'm doing this because this is the general situation. If you have multiple denominators, this is the ideal thing. But in this case, it's probably easier to just move the 3 over and you multiply and so on. Okay? I want to stick to this because this is in general the ideal way of doing it. All right, so I will be 3x minus 6 equals 5x minus 10. So this is 3x minus 4. And now move things around. So we get negative 2x is going to be equal to negative 6. So dividing by negative 2, we get x equal 3. Okay? All right. Questions? All right, good. And then the last one. What is it? X over x minus 3 minus 9 equals 3 over x minus 3. All right, what's the LCD here? Oh, wait, I didn't, I mean, you don't have to, but let me just keep the, so what was the restriction for number 8? So 2, right? So x cannot be 2. So here, what's the restriction? 3. So x cannot be 3. Okay, whatever we do, we cannot get 3. All right, what's the LCD?
X minus 3.
X minus 3, good. Notice that x minus 3 is the same guy in both cases, so that's fine. So multiply everything by x minus 3. All right, who can tell me what we get in the next line? After we multiply by x minus 3, what should I write? Yeah.
X minus 9x plus 27 equals 3.
So x minus, okay, so I'm gonna, let me just write like this and then we do that in the next step. So when you multiply, this cancels this, so you get x, then the x minus 3 times 9, and then equals 3. Okay, good. Now we do what your classmate was saying, distribute, so we get negative 9 plus 27, right? Equals 3, and then we solve. So what is this? So negative 8x. I'm gonna go ahead and already move the 27 over, okay? So we get negative 24. So what do we get for x?
3.
So we get x equal 3. Are we done?
No.
Is this a solution?
No.
Why?
Because of the restriction.
So that's exactly the restriction. So remember, what's going on is that we are multiplying by this quantity and we are modifying this equation into this one. Now, we turn this equation into something that has no issue, right? If you know the first line, you look at this line, this is a perfectly fine equation. There are no problems here. To solve it, and this x equals 3 is the solution to this line right here, the second one, okay? But to understand, this is not the original one. The original one is this one. And this one comes with a restriction. And this is exactly the value that x cannot be. Okay? So, because this is a restriction, then you say, well, unfortunately, we need to ignore this because x cannot be equal to 3. So, what's the conclusion here? So we have no solution. Okay? So we have no solution. In this case, this value, x equals 3, this is called an extraneous solution. We call that an extraneous solution. Extraneous solutions are going to pop up also when we talk about radical equations. Okay? So typically, when you do this kind of process that you modify your equation, you turn it into something that is fundamentally different, like it goes from rational to linear, or from radical to quadratic, and that kind of stuff, when you modify an equation, it could be that extraneous solution show up. Okay? Moving things around, that's okay. But when you do something more drastic, like multiplying or squaring both sides and that kind of stuff, then you can introduce extraneous solutions. So you have to be mindful of that. Okay?